This video lecture is about the other galaxies in the universe.
The lecture outline starts off with how we know these fuzzy objects are actually separate entities apart from the Milky Way. Because just by looking at them through the telescope, they could be small nearby things like forming planetary systems within the Milky Way, or they could be large, faraway things outside of the Milky Way. Like we had to do with the planets and with the stars, in order to compare these fuzzy objects with each other and with our home galaxy, you need to measure the distances to them. Just about everything in astronomy starts with the distance. Milton Humason and Edwin Hubble solved the question of what are these spiral nebulae in the 1920s by finding distances to the nearby galaxies, starting with the Andromeda Galaxy. Guess which type of important variable star they found in the mid-1920s residing in the Andromeda Galaxy? Cepheid variables. The distance derived for the Andromeda Galaxy from the period luminosity relation of Cepheid variables and the inverse square law was much too large to be inside even the largest possible size considered for the Milky Way. It was a separate galaxy. Other fuzzy patches turned out to be also very far away, well outside the Milky Way. We now know that the Milky Way is just one of many billions of galaxies in the observable universe, and is in a typical spot in the universe. Step by step, we have followed the directions set out first by Nicholas Copernicus over 400 years ago of removing us from a special place in the universe. The Earth is not the center of the solar system. The Sun is not at the center of the galaxy. And our galaxy is tucked away in some nondescript corner of the universe. Next slide. A decade before Humason and Hubble were finding distances to galaxies, Vesto Slipher found that over 40 of the fuzzy nebulae had redshifted spectra, which meant they were moving away from us. Using Cepheid variable distances coupled with Slipher's Doppler shift measurements, and some others of their own, Hubble and Humason discovered a surprising relationship when speed was plotted versus their distance. More distant galaxies have larger redshifts, which means more distant galaxies are moving faster away from us. 2 years before Hubble made their results public, Georges Lemaitre in Belgium predicted such a relationship should arise as a result of Einstein's theory of general relativity. Hubble did a much better job in publicizing his results, so the relationship was called the Hubble Law for many decades, and it wasn't until 2018 that Georges Lemaitre contribution was finally recognized and the relationship was renamed the Hubble-Lemaître Law. At first glance, it seems that we're at the center and we've committed some galactic error of behavior, so everyone's moving away from us. But no, the Hubble-Lemaître Law shows, in fact, that the universe is expanding uniformly. Every galaxy cluster is moving away from every other galaxy group, so every galaxy sees the same Hubble-Lemaître Law. There is no galaxy at the center of the expansion because there is no center to the expansion. This illustration shows what's going on. The space between galaxies expands by the same factor, so for example, every 10 megaparsecs of distance becomes 15 megaparsecs of distance in a given time interval. The galaxies are carried along with this expansion of the entire coordinate system, or grid work. The figure also shows that the space inside a galaxy, or even inside a galaxy cluster, does not expand because the internal gravity of the galaxy and of the galaxy cluster members for each other overcomes that Hubble-Lemaître expansion. This is why the Hubble-Lemaître law applies for only the very large distances. The next figure shows a two-dimensional example of the Hubble-Lemaître law and how with a uniform expansion, every galaxy is going to see the same expansion factor, and that galaxies farther away will appear to move faster away. One last thing before we move on. Because more distant galaxies are moving faster away from us, it means that when we look at galaxies with large redshifts, we are seeing them as they were long ago. Next slide. This slide shows the three basic types of galaxies as classified by Hubble: ellipticals and spirals, which could be regular spirals with arms coming right out of the nucleus, or from the ends of a bar of gas and dust going through the center, and a catch-all bin for all the ones without definite structure, called the irregulars. At the time Hubble came up with this sequence, it was thought it might show how one galaxy could develop into another type of galaxy. We now know that galaxies left alone will not turn into another type of galaxy. Spirals have nearly circular star orbits with only slight tilts. They still have plenty of gas and dust in their disks for star formation to occur at a slow but fairly steady rate in their spiral arms, and the hot luminous stars outline the spiral pattern in their disks. Ellipticals have star orbits with a wide range of eccentricities and tilts. They used up their gas and dust in a burst of star formation long ago, and they have a more rounded shape. The irregulars still have plenty of gas and dust for stars to form in patches randomly across the galaxy. Many of the irregulars are now undergoing a burst of star formation, which makes them easier to see. We now know that galaxies left alone will not turn into another type of galaxy because each type of galaxy has very old stars. The oldest stars in any galaxy all have about the same age of around 13 billion years. This means that spirals form as spirals, ellipticals form as ellipticals, and irregulars form as irregulars. The key phrase here is left alone. Galaxies do like to group together, and they can bump into each other. Next slide. Galaxies love to cluster together. Their mutual gravity can draw galaxies together into a cluster that is several millions of light years across. The Milky Way is part of a small cluster of 50 to 100 galaxies called the local group, about 3 million light years across, with the largest members, the Milky Way and the Andromeda Galaxy, at opposite ends of the local group. Most of the galaxies of the local group are small dwarf galaxies of a few 100 million to a few billion stars each. Galaxy clusters attract each other to produce superclusters of tens to hundreds of clusters. Their mutual gravity binds them together into long filaments, thin string-like structures, 300 to 900 million light years long, 150 to 300 million light years wide, and 15 to 30 million light years thick on average. Recall that about 3 light years makes 1 parsec. The discovery of these huge structures was made from years of taking Doppler shifts of thousands of galaxies. The Doppler shifts of the galaxies were converted to distances using the Hubble-Lemaître Law. Between the filamentary superclusters are huge voids with very few, if any, galaxies. The voids are typically 150 million light years across. What all the large-scale surveys show is a lacy web-like structure to the distribution of galaxies, which is really obvious in the cosmic web link. You can think of the large-scale structure being like soap bubbles with the galaxy clusters along the boundaries, where the bubbles touch, and the voids being the inside of the bubbles. There are no larger structures than superclusters. Compared to the size of individual galaxies, the galaxies that are members of a cluster are not that far apart from each other, just a few galaxy widths from their neighbors. That means they're likely to bump into each other sometimes over the past several billion years of time. When galaxies collide into each other, their stars don't hit each other because the stars themselves are mere pinpricks compared to the distances between the stars. The gravitational field of the galaxies are really messed up, so the star orbits are greatly distorted. The molecular clouds, though, are many light years across, so the molecular clouds of one galaxy will bump into the molecular clouds of the other galaxy. As the molecular clouds hit each other, they compress and produce a large amount of stars in a short time frame, like a bunch of fireworks going off at once. Astronomically speaking, of course. These collisions take place over hundreds of millions to billions of years, so we use supercomputer simulations of the gravity and gas dynamics to model what happens. The Andromeda Galaxy actually has a blue shift instead of a red shift, and it will collide with the Milky Way in a few billion years. Hundreds of supercomputer simulations show that spiral galaxies are relatively fragile, so the spiral structure is disrupted when spiral galaxies crash into each other. The result is often something that looks like an elliptical galaxy. A small galaxy punching through the middle of a spiral galaxy can make a ring galaxy. Large spiral galaxies hit by small dwarf galaxies can still often maintain some sort of spiral structure. Check out the videos of galaxy collision simulations. There are other links in the textbook website. At the centers of rich clusters of galaxies, those made of thousands of galaxies, we find giant ellipticals with trillions of stars that have multiple nuclei, which are all that remain of the galaxies that were cannibalized. M87 in the Virgo cluster shown here is one example. The rich clusters have their spiral galaxies all at the outer boundaries of the cluster because the spiral galaxies that were closer to the center had their spiral structure destroyed with all the collisions going on. When we look to very great distances, we see galaxies with a lot more distorted structures. That's because we are seeing the universe as it was long ago when galaxies were closer together, and there were more collisions happening than now. Our own galaxy, the Milky Way, has cannibalized several or many smaller galaxies in its lifetime, so it is now a fairly large galaxy as far as galaxies go. But it is still much smaller than a typical giant elliptical galaxy like M87 at the core of rich galaxy clusters. Galaxy collisions will dump gas and dust into the compressed cores of galaxies. The great majority of galaxies have a supermassive black hole at their centers, so all that gas and dust being dumped into the galaxy cores can create all sorts of activity, which is the subject of the active galaxies lecture in this set.